Hello everyone, I'm Sathwika. This video is about a case study in financial machine learning, that is derivative pricing. We are going to look into the intro, the problem statement in derivative pricing, feature engineering and selection, model selection and evaluation, model development and monitoring, and challenges. In this case study, we explore derivative pricing using machine learning models. Traditional models like Black-Scholes are computationally intensive and rely only on the assumptions that may not hold up in real-world scenarios. Machine learning can potentially offer more flexibility and accuracy by reducing these assumptions and enhancing computational efficiency. Problem statement. Our main objective is to use machine learning to predict derivative prices based on key financial indicators like stock price, strike price, time to maturity, and volatility. To achieve this, we used a synthetic data approach based on the Black-Scholes model, allowing us to stimulate option prices for the model training, feature engineering, and selection. To improve model accuracy, we engineered new features from existing data. Using techniques like univariate feature selection, we identified relevant features including moneyness and time to maturity. Scatter plots and correlation matrices helped us to visualize the relationships between the features and the target variables, aiding in the feature selection. Model selection and evaluation. We evaluated various models, including linear models like linear regression and nonlinear models like random forest and gradient boosting. Using metrics like mean absolute error, that is MAE, we identified the best performing models through k-fold cross-validation, ensuring robust model performance. Model development and monitoring. After model selection, we focused on training and monitoring the model's performance. Data preprocessing, normalization, and model training were key steps, followed by real-time monitoring using matrices like MAE. Challenges. There can be challenges with data quality, model assumptions, high computational demands, complex feature engineering, and the risk of overfitting. Addressing these is crucial for the future improvements. Next up, let's see the demo of the technical implementation of our case study, that is, technical implementation of derivative pricing using machine learning models. Hello everyone. I'll be presenting a demo on machine learning based approach to derivative pricing. Our goal is to predict option prices by learning from the Black-Scholes model through supervised regression. To start, we import the essential libraries for data handling, visualization, and modeling. These include NumPy and Pandas for data manipulation, Matplotlib and Seaborn for visualization, scikit-learn for machine learning tasks. Installing these libraries provides tools for machine building, parameter optimization, and advanced statistical functions, which will be central to our derivative pricing model. Next, we import the warning libraries and disable any warning messages. This step is essential to keep our notebook output clean, uh, focusing only on the critical results. We then initialize model parameters for our option pricing model, defining values such as true alpha, true beta, true sigma, and risk-free rate. These constants stimulate market dynamics for options pricing. Here, true alpha and true beta are the constants basically which influence option pricing volatility as per the Black-Scholes framework. And true sigma acts as a baseline for the volatility, and risk-free rate represents the baseline interest rate used in options calculation. Now we define a function called option vol from surface. This estimates the option volatility based on moneyness and time to maturity. This function adjusts volatility in response to the options market positioning, relative to its strike rate. Here, moneyness is basically the ratio of the current asset price to the strike price, and time to maturity represents how close the option is to its expiry date. Volatility output is calculated based on these factors to stimulate market variance for different conditions. And then we have a function called call option price. It's a function based on Black-Scholes formula. This function computes the theoretical option prices by calculating parameters D1 and D2. Here, D1 and D2 are basically the intermediary variables in the Black-Scholes formula used to calculate cumulative distribution values. And call price represents the final output of this function, indicating the estimated price for the call option under the given parameters. And then comes the data generation. In this part, we generate a simulated data set with various values for moneyness and time to maturity. This data will help us to build our model by capturing option pricing under different market conditions, market risks. Next up, we have EDA, that is exploratory data analysis. We explore the data to understand its structure and the distribution of values. Here we have used head function, which shows the columns that are present in the data set, that is price, moneyness, time, and vol, which is volatility. And then we have the description function. Description function basically describes the columns. We have count, that is the number of entries in each column, and then we have mean, that is the average value of each column, and then we have standard deviation, and then we have minimum value to each column, and 25 percentile, 50 percentile, 75 percentile, providing insights into the data distribution. And then we have maximum value in each column. Next up comes the data visualization. In this phase, we analyze our dataset to understand how each feature, such as moneyness, time to maturity, and call price, relates to each other. This helps us identify the patterns that will guide our model's approach to option pricing. First, we have a histogram here. This histogram displays the frequency distribution of moneyness. The shape of this distribution reveals where most options fall relative to their strike prices, highlighting market tendencies in this dataset. The peaks at certain values indicate common market behaviors. And then we have another histogram for time to maturity. This histogram shows how the duration until an option's expiration is distributed across the dataset. Clusters in specific ranges indicate typical expiration period for these options. Basically, this histogram that visually summarizes the time to expiry distribution, which can highlight any tendencies towards shorter or longer maturities. We can see that the price has an interesting distribution with a spike at zero. And then we have correlation metrics. Correlation metrics quantitatively shows the strength and the direction of the relationships between features like moneyness, time to maturity, and call price. This metrics is essential because it helps us to identify which features might most significantly impact call price. In this matrix, basically the values range from -1 to +1. Values close to +1 indicate strong positive correlation, which means as one variable increases, so does the other. And the values near -1 suggest strong negative correlation, which means one value if one value increases, the other value decreases. And the values close to zero implies little or no linear relationship between the variables. Here we have high correlation of 0.87 between moneyness and call price, which indicates a strong positive linear relationship. This means that as moneyness increases, the call price also tends to increase significantly. And then the correlation of 0.44, that is between the time and the price, that is time to maturity and call price, is moderate. This value suggests a positive but weaker linear relationship between uh, uh, time and price compared to moneyness. Although options with longer time to maturity generally have a higher price, due to the added time value, this relationship is less linear as other factors like market volatility play a role. And then we have low correlation between moneyness and time to maturity, which suggests almost no linear relationship between these two features. This aligns with the theoretical expectations as an option's time to maturity does not directly determine its moneyness. And then here we have scatter plots. We use scatter plots to further examine the pairwise relationship, especially focusing on how moneyness and time relate to call price. First, we have this called scatter plot, which demonstrates how call price changes with moneyness. Typically, as moneyness increases, call price tends upwards as higher moneyness means the option is more likely to be profitable. The data points from an upwards trend, visually confirming the positive relation indicates in the correlation matrix. And then we have a scatter plot, which shows how price varies with the time. Options with longer times to maturity tends to have higher prices due to the extended opportunity for the profit, a key insight for option evaluation. Next up, we have data preparation and analysis. In order to do this, first we have to do feature selection. In this step, we used select k-best to identify the most predictive features of our model. Select k-best with F regression scored each feature's correlation to option price, ranking them by importance. Here we have formatted the data, that is, we organized the scores with feature names uh, like moneyness, time, that is volatility, for easy comparison. As a result, moneyness emerged as the top predictor, confirming its role in the option pricing. Next up, we have evaluate algorithm and models. Here, we start by splitting our data for training and testing, setting aside 20% for the validation because we have defined the validation size of zero point 0.2, then split X and Y into training and testing sets. Next up, we have cross validation setup. That is, we are using 10 fold cross validation as the number of folds is equals to 10 with the negative mean squared error to rank the models. To compare the models and algorithm, our models include linear regression, decision trees, support vector regression, neural networks, that is MLP, etc. And ensemble methods like random forest regression and adabust regressor. In this part, we focus on evaluating boosting and bagging methods, then perform model comparison using k-fold cross-validation. Boosting is basically it adds the models in sequence, each focusing on errors of previous model. In boosting, we use AdaBoost regressor and gradient boosting regressor. And bagging is nothing but it builds multiple versions of a model on random subsets, then averages the prediction. For this, we use models such as random forest regressor and extra trees regressor. And then we have cross-validation setup. That is, we perform k-fold cross-validation with number of folds, that is 10, and set scoring to negative mean squared error to compare models. For clarity, we convert opposed to positive mean squared error because lower values indicate better performance. Here in the training, we fit on X train, then calculate MSC between predictions and actual values. And then in the testing results, we predict on X test and compute mean squared error to evaluate generalization. This code basically creates a box plot to visualize the k-fold cross-validation results across all models, with each model representing by a box, as you can see. Models with lower and more compact boxes have better and more consistent performance. This plot helps quickly identify which models are performing well in cross-validation and which may be inconsistent across flows. In this output, we can see that MLP, random forest, and possibly caught to have lower MSC, that is mean squared error, and less variance compared to the other models. To refine the to refine the view, we removed lasso and elastic net models, which performed less efficient. And this bar chart gives a side-by-side comparison of training and testing errors for the remaining models. We can see MLP stands out as the strong candidate, justifying its selection for further fine-tuning in the next step, which is grid search. We do grid search in model tuning and finalizing the model. We define our parameter grid, which includes different configurations for the number of hidden layers and neurons in each layer. As we can see here, we tried single hidden layer with 20 neurons, a single hidden layer with 50 neurons, two hidden layers with 20 neurons each, and more complex configuration with three layers consisting 20, 30, and 20 neurons. Here we initialize the MLP model. With the model trained, we generate predictions on our validation dataset and X-test. Next up, we calculated the mean squared error between our predictions and the true values in y-test, which gives us an indication of how well the model is performing. Hence, the deep learning models does an excellent job by fitting the Black-Scholes option pricing model. The accuracy may be enhanced with more tuning. As a conclusion, by simulating market data and applying machine learning models, we have built a predictive model for derivative pricing. This approach can flexibly adapt to various market conditions, providing robust price predictions.